Hello, so today we only have to see these last theorems for this chapter. Okay, so we have the Green-Riemann theorem and how we can apply this to area calculation, and we will be done with these lecture notes. All right, so let's have a look at this Green-Riemann theorem. So, what is this is the theorem that is going to link the line integral on the boundary of a domain and the double integral related to a domain, right? So, what do we need? We need some domain that is going to be called U, and it has a boundary. Usually, the boundary is denoted with a delta letter U. So, what does it look like? Looks like, well, whatever u looks like, this is u, and that would be the delta of u. Okay, so well, let's assume that this delta of u can be described by a parametric curve. So usual notations, it's going to be described by x of t, y of t. Okay, so the contour of this domain can be described by a parametric curve. In that case, what is the theorem telling you? Well, another hypothesis is that you're given some vector field P and Q, and it's of class C1. What does that mean? It means that P and Q are continuous and both their partial derivatives are also continuous. Okay, so everywhere on this domain and on the boundary. So the theorem tells you the following thing: the line integral, well, the usual one of on the boundary of u, so delta u, p dx plus q dy is going to be equal to the double integral. Okay, so that's a double integral. So dx dy of the following thing: dq over dx minus dp over dy. Okay, first thing that we can note is that those two partial derivatives that we have here, okay, these are the ones that we use in order to compute that whether we have a conservative vector field, okay, and so that we find indeed what we expect. You know that if PQ is conservative, you know that the line integral depends only on the boundary, on the values at the bounds of your line, and if you have a closed line, then you will get 0. So that if your vector field is conservative, you get that dq over dx is equal to dp over dy, so that this is going to be equal to 0, and we get what we expected. We find that this line integral is equal to 0. Okay, good. This being said, let's see why that would be true. Let's make some kind of a proof, well, at least in some simple case. Okay, let's see that. So the Green-Riemann formula, so we want to prove that we've got this thing. So the line integral on delta u of p dx plus q dy, as always, is going to be equal to the double integral of dq over dx of xy, of course, minus dp over dy of dx, well, xy dx dy. Okay, so more precisely, what we're going to do is we're going to show that that part with the p part is going to be equal to the p part here, and secondly we will show that well, similarly we could show that the q part here is going to be equal to the q part here. Okay, so let's do it at least on some example that is slightly simpler when we can describe our domain. So let's assume that you're in R2. And you have a domain that can be described as you would have you can get two curves. Okay, so here I drew something quite regular, but you could imagine things that are less regular. But what I want to do is that I want to have two curves, one curve gamma 1, one curve gamma 2, so that delta u is going to be the union of gamma 1 and gamma 2. Okay, and the thing is that if that is x and that is y, you can describe gamma 1 as y is equal to some function of x. So let's say this is y1 of x, and you can describe gamma 2 very similarly as by saying that y is some second function, let's say y2 of x. Okay, so that curve is y1 of x, and that the curve on the top is going to be y2 of x. Right, and they meet at 2 points, and then, well, if you take the union of the two curves, you get the whole stuff of gamma. Okay, so that's if ever you had some vertical parts so that you wouldn't be able to make it a curve, or you would need, if you have something more complicated as a domain, you could cut that into several parts, and so, well, that would just be a generalization of what we're going to do. Okay, so let's work on the p part, right? So let's see what it gives me if I'm doing the double integral on that domain u of dp over dy of xy. Okay, so assume that p was a c1 scalar function of two variables, and so I can compute the double integral of dp over dy of dx dy. Okay, so maybe we should give some more precise names. Let's say this is a and this is b. Okay, so if you remember what we said, well, it's just going to be I can relate the area below the curve gamma 2 and the area below the curve gamma 1 to the area inside of this domain U. Okay, so that's well, the below the, okay, so what would I get? I would get, so that's going to be the integral from a to b, so the x is going from a to b, and the y is obviously going to be between y1 of x and y2 of x of, well, my usual function dp over dy of xy dy dx. Okay, so I need to do this in that order because this is how I could describe my domain. Okay, this is related to the first steps we did on double integral. Good news is that, well, my the function inside is already a derivative as a function of y. So that's just going to be given by, so let's keep the first integral, and the second integral is just simply solved as p of x y between y1 of x and y2 of x dx. Okay, and so that's just going to be equal to, if I expand that, that's going to be equal to the integral between a and b of p of x y2 of x minus so dx, well, let's cut that into two pieces, minus the integral between a and b of p of x y1 of x dx. Okay, so maybe you can remember that this is exactly a line integral. This is actually denoting the line integral on the curve that is described by, let's call that gamma 1 of, if I, well, my parameter is obviously x, gamma 1 of x, which is described by x is equal to x, and y is equal to y2 of x, and x belongs to AB. Okay, so if you remember that what we, this is exactly the line integral on that curve. And what is the curve that we are describing? We are actually describing, so let's see. A and B, and we are describing that thing, x, y2 of x. Okay, so this is the upper part. Sorry, that's this upper part, that's the gamma 2 of x, but in the direction, in the clockwise direction. So that's exactly the line integral on gamma, sorry, let's call that gamma 2, that would be a bit more adequate, okay? But that's the line integral in the clockwise sense, okay? This is, I'm going from that point to that point, like this, right? And this is the line integral. Very similarly, what I have here, the second one, okay, well, let's not consider the minus to begin with. So this is also going to be a line integral on something that is described by x, y1 of x. So obviously that's going to be this one. And I'm going from A to B. Okay, so this is the one in that direction. But with a minus in front of this, if I consider the minus here, this is not this direction, this is going to be in that direction. So actually what I have here, this double integral in P is going to be, so that one, dp over dy, that's just going to be, so dx dy, on my domain U. That's exactly the line integral on gamma, on delta U, on my whole boundary, in the clockwise sense, in the clockwise direction. Okay, now you can do exactly similarly the same stuff for the Q integral, and very similarly you will obtain, okay, similarly we will obtain that dq over dx, sorry, the double integral on my u of dq over dx. Well, you have to do something very similar if that's your x and your y, and maybe that was your domain. You will need to cut that into two parts, okay? One part that is describing, so let's say that this is x2 of y, and the other part that would be x1 of y, and maybe that's a good exercise for you to try. What you will get is that you will obtain that this is the opposite actually of the line integral on du, on delta u. Sorry, I've written one too many integrals, so let me erase that. Okay, on delta u of q dy, okay, but in the clockwise direction. Okay, and then if we if we add the two integrals that we obtain, we get that dp over dy minus dq over dx dy is going to be equal to the line integral on delta u of p dx plus q dy in the clockwise direction. Oh, sorry about this. In the clockwise. And if you want the contrary, so how was that given in the we had actually the opposite. Why? Because usually we always consider the positive trigonometric sense, which is the anti-clockwise sense, which is the trigonometric sense. Okay, so this is something that you have to keep in mind. So, if you compute, well, if you just want to do it in the anti-clockwise direction, you have to take the opposite of all that's preceding. Okay, so that's kind of a proof in some well, maybe simple case because the domain doesn't is not too complicated, and you can easily just choose two parts of a curve to describe it. If you had something more complicated, you could still do that, but we would need to cut that domain into as many pieces as necessary. Okay, thank you. So next is just going to apply to use that in order to do some area calculations.